in the Russian thermal reactor. But the problem here is the fast reactor irradiations that we use to generate this data point required about 8 years of irradiation. And if you remember, what I said is, if we had enough good data over a wide enough range, that range being about 10 to the minus 4 to 10 to the minus 2 dPAs per second, we should be able to actually generate an equation and be able to sort of skip, at least initially, the fast reactor data. Of course, eventually, if we had fast reactor data, we could add it to this data and get an even better extrapolation with a lower uncertainty and extrapolate to the thermal area. But when you consider that a lot of new materials that might be going into fast reactors right now have not been fully tested, particularly if they are ferritic steels, which have long incubation periods, one could imagine that any data that any reliable data that you collect with ion beams in a period of a few months would be very, very valuable, even if the error propagation would be as much as 10 or 15%. So here is a tool now that potentially exists for doing rapid evaluation of swelling of new materials for reactors. So I said I was going to give you some examples. And the first example I want to give you was the one that we just looked at before, where we actually saw in this set of data from Okita, we saw over a factor of 20 the change in the swelling as a function of, as I said, a factor of 20 change in the dpa rate. Now, remember that the swelling equation that I have is right now for 321 stainless steel. Iron, chrome, nickel, iron 15, chrome 16 nickel isn't 321 stainless steel, but I did something with it which you shouldn't do at home. Okay. I modified it, and I can explain afterwards if anyone wants to know how did I modify that swelling equation. I modified it so it represents iron 15, chrome 16 nickel. Trust me, Froggy, it's okay. But one thing I know is that I am fairly close to the edge of the swelling curve here. And again, that comes from analyzing this, looking at it carefully. And I also know that I can't get accurate results if I'm in the transition or incubation region, because that isn't handled correctly by the Kalchenko model. Again, I remind you that that can be fixed. So what we want to see is, can we predict the swelling at the ends of these curves here? Okay. And remember, this rule of thumb about 1% per dPA we're going to smash that rule in a moment. So here we go. That's what you get. So this is a modified 321 stainless steel swelling equation that's been modified to look like iron 15 chrome nickel. Okay, and here's how we are able to explain this data which had never been explained before, even though it's been in the literature for many years. Okay, I'm going to give you one other example. I have half a dozen other examples, but this one I like. I mentioned earlier the bolt swelling problem, and as a result of the bolt swelling, the bolt cracking problem, which some people believed at one time might be related to differential expansion between the former plates and the bolt material itself, which were different materials. One was 304 stainless, and the other was, I think, a 316. No, it's a, yeah, 304. Yeah, the other material was a 316 stainless. So this review by EPRI was commissioned, and this sort of became the gold standard of what was going on with regards to swelling of 304 stainless steel at very low dose rates in the baffle assembly. The baffle assembly is outside the core. I was interested to see if we could fit that data. And again, I shouldn't be able to fit it in the transition region because the Kalchenko model doesn't handle the transition region correctly. But I should be able to fit it here. And so again, I modified the 321 stainless steel to look like a 304 stainless steel by shifting the Monsoor line and adjusting the incubation period, and voila. But then we went down and gave EPRI a briefing on this, and they said, oh, this report is invalid anymore, and we know the numbers are really different. And I said, I wonder how that could be. So I went home and I said, well, look where this is happening. It's happening right on the edge of the swelling curve. How sensitive are we to temperature? So there it is. You change the temperature by 15 degrees and you double the swelling. And that's what happens if you're on the edge of the swelling curve. So then you have to raise the question, how accurately were these temperatures actually known? Because a 15-degree error is not unlikely. And of course, it can go the other way. The curve could just as well go that way and get half that amount. So temperature measurements are critical. How critical? The swelling, if you have an accurate swelling curve for the material at hand, you can actually analyze these uncertainties with some precision. Okay, so what have we learned? Well, everything that you've learned today, I like to refer to as the Tantalus effect. The faster you try to do these experiments, the more the data runs away from you, just like Tantalus, okay? So to study bias-driven swelling, you must track the peak and shape of the swelling curve. But increasing the dpa rate has multiple effects. The incubation dose increases, so it moves away from you. The peak in the swelling curve moves to higher temperatures, it moves away from you. The width and shape of the swelling curve narrows, it gets smaller. The peak of the swelling curve decreases, it gets smaller. The percent swelling per dpa decreases, it gets smaller. So doing ion beam experiments is a non-trivial effort because you have to go to higher doses, higher temperatures, and of course, you have to do things over a wide range of dose rates, wide enough so that when you do the extrapolation, your experimental errors don't propagate so badly that you get meaningless data at low dose rates that are relevant to reactor conditions. So the incubation dose is both temperature and dpa rate dependent. We know that now. DPAs at different dpa rates are not equivalent. The literature is filled with comparisons. I did this experiment to this number of DPAs, and then I did another experiment over here with a different reactor, with ion beams, and I did it to the same number of DPAs, and I compare the two, and they don't look anything alike. And that, of course, they don't look alike, and there's tons of this in the literature. If somebody doesn't tell you the rate and the temperature, and in fact, in reality, if they don't tell you what the swelling equation is, you don't know what you're looking at. So the underlying rate theory physics is what connects swelling at different dpa rates, and one should say at different temperatures, through a single swelling equation, the ring. The impact. Irradiation times of weeks, not decades, to do testing of swelling. Possible extension to other damage accumulation mechanisms, for example, creep. Importantly, if you have the swelling equation for a particular material, you provide the kernels for FEA codes with impact on things like life extensions, relicensing of existing reactors. As I said, this is an important thing for the materials that are in the existing fleet of reactors, and for new materials, qualification and insertion. For example, ATF materials. Now, there's a caveat here that for ferritic, everything I've been talking about has been for austenitic materials. For ferritic materials, the incubation periods are very long. Okay? But again, one can see how ion beam experiments could be very valuable here, because the time in a fast reactor is still going to be very long. And if you want to get that data and you're designing a reactor and you want to reduce your uncertainties and financial risks, the way to do that is to carry out ion beam experiments over a wide range of dpa rates. Go forward challenges and needs. Improvements in the analytical methodology are needed. The swelling during incubation is not accounted for in the Kalchenko method. You need a more accurate definition of the incubation dose and therefore of the transition region. We need to make contact with cluster dynamics modeling, which is really rate theory on steroids. We need to do accelerated ion beam testing over a wide range of dose rates, and one of the problems is people who have accelerators don't like to do experiments at 10 to the minus 4 because that takes weeks, and they have lots of different projects and people are using the accelerators, and they like to see people go in and get out in a period of hours or days, while this requires weeks. So it really requires a dedicated facility with 24/7 operations for long irradiations as well as the short irradiations, with careful attention to the quality of the irradiations. Like one of the problems quite often in ion beam irradiations is recoiled carbon contamination coming from the surface of the specimens. The ion beams push the carbon in and you end up with carbides in the material, and you get the wrong mechanical properties, you get the wrong vacancy and interstitial migration, et cetera, et cetera. So you really have to worry about the quality of the radiations. And then, of course, as I said at the beginning, at the end of the day, even if you do the irradiations faster, you still have a lot of PIE, and you need dedicated FIBs, high-resolution microscopy, and micromechanical testing to handle all of the specimens that come from doing these experiments at such a high dose, at such a high data rate. So there's a large amount of data that usually would take decades to accumulate, which you're now collecting in a period of weeks, and that puts a big stress on your post-irradiation examination. So, thanks for your attention, and remember to follow the peak in the swelling curve.
You are plotting two measured quantities and one calculated quantity. So I'm suspicious of the calculated quantity, and that's dpa. There's been the different models, different values of dpa and flux that have come out from the different models. And so since half your data set is high and half in the lower end, in different particles, it kind of reminds me of a postdoc. They do a little more organized work between data taken before lunch and data taken after. And I was wondering whether you have any comment on that.
There's a handful of experiments where shrim has been calibrated over wide dynamic ranges. I don't remember the references off the top of my head, but where the displacement rates have been measured and cross-calibrated with snook peak measurements and resistivity measurements. So we can go to those and look and ask the question of whether or not a shrimp-type billiard ball binary collision calculations are adequate over that range. Because there's the conversion from the neutron flux to the shrim that you have to always worry about. However, I can sort of hang my hat on the fact that when I showed the Mansour line for the austenitics, they sort of looked okay and had a similar quality factor as the copper and nickel data. So insofar as the Mansour curve is being followed, you could say that's the test that you are actually doing the dpa calculation, correct? But I don't dismiss what you say.
Well, Gary Watts' book has some examples of competing theories of dpa dose rates. And in a competing field of health physics, I noticed one year they neatly changed the RBE for fast neutron effect factor of 2. So I wonder if material science is in that same level of fog.
Yeah, there's also a well-known, discovered a few years ago, problem in shrim. When you try to run shrim in the full mode, it actually falls on its face completely. And there's a hidden bug that nobody seems to want to find. So
it's hidden bug is H.
So, but there are other binary models out there that seem to be better than shrim. But I'm not dismissing the issue that always has to be dealt with.
Yeah, well, if your data is organized by type of particle and also then this great chasm between what the ferrites do and what the austenites do, then that makes me wonder whether there's something more fundamental at work.
As I said, right now I would hang my hat on the Mansour formulation. That if you can get a Mansour-like terms of a logarithmic relationship over the full dynamic range, 10 to the minus 9, 10 to the minus 2, you're probably in the ballpark.
I think that, thank you for the talk. So I was thinking about a problem, which is a real problem. You know, the French, they're building this reactor ECR. You're probably already aware that the pressure, the reactor pressure vessel, the head and the bottom have higher content of carbon in that steel. I mean, the safety regulator comes in and say, okay, since you have a higher carbon, your resistance to the toughness is going to be affected. You get a crack. The ability to stop the propagation of the crack will be affected. So, what do? These are very, very expensive items. Take a lot of money to make that vessel, the head, and in fact, one of the reactors is currently operating with that, supposed to be deficiency, because we do not, there's not enough data to know the carbon content, the higher carbon content effect on that. Not get the swelling problem yet, because I think that they wanted to stop operating this reactor in 6 to 7 years and see whether they can, and then inspect it. That's a very high, very expensive undertaking, because EPR is supposed to be the French Gen 3 reactors. This problem could kill the entire campaign. Yeah. Have you ever thinking about the simple equation that you have? Since you mentioned about carbon is an important, contaminant or
well, I was still referring to carbon as a contaminant in ion-beam irradiations, but
you already have a higher content of carbon in the steel.
Yeah, right. So the thing is what's the risk-benefit issue that you're dealing with? That's what I was trying to point to. If what I've talked about makes any sense, that you can in fact do swelling studies at high dose rates that have engineering value at low dose rates, then even if the error bars are significant, more so than if you had just done fast reactor irradiations over a period of several years, that would be valuable if the risk that you're dealing with in terms of the materials type is high enough. If, on the other hand, it's a research reactor where you design things so that you can take out components that you're uncertain about, then that's fine. I mean, when the reactor industry first started, there were 50 test reactors that were going along with the one reactor we were building every month or two. A lot of those test reactors went critical once or twice, and then they learned something, and that was the end of that reactor. But we don't do that anymore. And so we wait, we run to failure. And the classic example is the bolt problem, is the bolt cracking problem, where the dose rates were very low, okay, but there's significant gamma heating and a corrosive environment and potential for differential swelling. And those problems weren't even understood at the design point, but then we're pushing those reactor lifetimes well beyond 40 years. And suddenly there's the problem. Now that problem could have been worked with regards to at least the swelling component and the corrosion component way back when, if you were willing to do those types of experiments. So,
yeah, well, that's another point, is that swelling curve is very close to politics because of the connection to lifetime extension.
Exactly.
All that.
Yeah.
A lot of people that would like their reactors to be
years for 40 years.
So
now people talk about
that swelling curve.
But now people thinking about put investment into this reactor only lasts for 7 years. That's a big difference. Or 6 years.
Let me define the big caveat in this whole thing. The idea that you can do, whether it's swelling or creep or some other material, let's stick to just vacancy diffusion phenomenon. So swelling and creep. The idea that you can do high-rate experiments that are meaningful in terms of generating an equation that's extrapolable to low dose rates is only valid if the set of differential equations that are being sampled at high dose rates is the same as the ones that will be sampled at low dose rates. If a new mechanism comes in as you're changing the dose rate, then, and you are way up here at high dose rates and the mechanism starts to appear at 10 to the minus 5 dPa, you're going to miss it and you're in trouble. And that's why A methodology like this needs to be carefully coupled with computational approaches where you can sit down and assume all the possible mechanisms that are going on and test the idea of whether those mechanisms are in fact being sampled at high dose rates or not. And that will also define at what dose rates do I have to go to actually make predictions about low dose rate environments. So it's really lies in what is the set of differential equations. If you went to Sandia Labs where they have a combustion laboratory, they write on the blackboard 150 different mechanisms that are happening in the cylinders of your car. And the question always is, which ones of these are on the critical path? That's the same thing we're talking about here. This is rate theory. And so everything hangs on real. So this is not just an experimental idea. This really goes to the heart of mean field theory. And today it's called dynamic cluster modeling or things like that. But it goes to the heart of that type of approach to the problems. Also molecular dynamics too.